Okay, let's dive right into this explainer. Today, we're going to learn how to decode the visual language of algebraic functions. I mean, if you've ever stared at a complex math formula and felt like it was just this random alphabet soup of letters and numbers, trust me, you are definitely not alone. But what if I told you that every single equation is actually a blueprint for a very specific visual shape? Well, today, we're going to unlock that mathematical sixth sense, and it's absolutely going to transform how you recognize and interact with functions. So here's our agenda for today. 1. Inputs, outputs, and ranges. 2. Decoding linear functions. And 3. Recognizing quadratic shapes. Let's get right into it.
Section 1. Inputs, Outputs, and Ranges. The machine.
Thinking of mathematical functions as a processing machine is honestly the best way to visualize what that algebraic notation is actually doing behind the scenes. So, to understand our machine, we need two absolutely critical pieces of vocabulary. The domain, that's exactly what you feed into the machine. It's your starting numbers. And the range is the set of outputs it literally spits out based on those specific inputs. So it's a simple cause and effect relationship. But as we're about to see, not every relationship makes for a working machine. Okay, take a look at the data here. We've got inputs mapping to outputs, but notice something a bit weird. A single input in the domain is actually producing more than one output in the range. And because of this specific relationship is not a function. Just imagine pressing a button on a vending machine, right? And it just randomly gives you one of two completely different snacks. No way! A mathematical function has to be predictable. One specific input can only ever yield one specific output. In this case, plugging in a 4 gives us both a +2 and a -2. The machine glitches out, so it's a mapping, sure, but it is definitely not a function. Now, let's look at a machine that does work, like the function x cubed minus 3x. This brilliantly illustrates how putting a physical boundary on your inputs, what we call a restricted domain, automatically limits the possible range of your outputs. If we let our domain be absolutely any number, an unrestricted domain, well, our graph just goes on forever, and our range includes all values. But if we clamp down and say, nope, x can only be between -2 and +3, then we effectively chop the graph into a distinct segment. Suddenly, our range is trapped. It's limited precisely from -2 to 18. So simply put, the domain dictates the range. Moving right along to Section 2, Decoding Linear Functions, the straight line. Let's see how our inputs and outputs build our very first visual code. Whenever you see an equation in this specific format, f of x equals ax plus b, your brain should instantly picture a straight line. This standard form is basically the blueprint for a straight line. And the letters A and B? Well, think of them as dials. Dials you can turn to change the picture. Everything about how that line looks is controlled right there in those two little variables. Looking directly at these graphs, the A value dictates the orientation, or the tilt of the line, while the B value shifts its exact position on the grid. For instance, a function like f of x equals x minus 3 gives you a specific slope, crossing the vertical axis down at -3. But change it to f of x equals 2x minus 4, and suddenly the line is way steeper, right? Because our A value increased from 1 to 2, and it crosses the axis even lower, at -4. You're quite literally just twisting dials and watching the line react. And hey, you don't have to just take my word for it. You can easily test this cause and effect relationship yourself by plugging linear functions straight into your graphing display calculator. Whether you're rocking a Casio or Texas Instruments, the steps are incredibly straightforward. You just select your graphing menu, type in your ax plus b equation, and hit graph. Honestly, it's highly recommended that you take a few minutes to just plug and play around with this. By keeping one value constant and tweaking the other, you can immediately see how the function physically morphs on your screen. Check out these two families of graphs. On the left, we kept the steepness, the A value, exactly the same, but we kept changing the B value. And the result? A series of perfectly parallel lines just sliding up and down. Now, on the right, we kept the B value identical, so they all cross the vertical axis at the exact same point, but we changed the A value. It looks almost like a fan opening up as the lines rotate around that one single pivot point. It's literally visual algebra in motion. All right, Section 3, Recognizing Quadratic Shapes. The curve. So now that we've totally mastered straight lines, let's level up our code breaking to quadratics. We are moving from straight, rigid paths to dynamic curves. Here's your new blueprint. F of x equals ax squared plus bx plus c. And here is the absolute golden rule. The exact moment you see that x squared in the formula, you instantly know the straight line is going to bend into a curve. As long as a is not 0, that tiny little exponent of 2 completely transforms the entire geometry of our graph. The crucial takeaway here is that quadratic graphs will always take on a characteristic U-shape or an upside-down U-shape. Take a look at these two graphs side by side. The one on the left dips down into a valley, and that happens when your A value is a positive number. The one on the right, it crests like a hill, forming an upside-down U, and that happens the exact instant your A value becomes negative. It's crazy, just a single negative sign completely flips the entire landscape of the graph. To summarize the whole quadratic code, look for that symmetrical curve and remember that tweaking your A, B, and C variables will stretch or shift that perfect arc. These curves are super elegant because they feature exactly one line of symmetry, right down the middle. Like if you folded the graph in half, both sides would match up perfectly. And just like our straight lines, A, B, and C are the main control dials for this mathematical shape.
For instance, if you isolate and change just the C value, watch how the entire family of parabolas drops or raises just like an elevator. Look at this stack of curves. By keeping the A and B values locked in place, the width and the left-to-right positioning stay exactly the same. All we did was change C. You know, the number just hanging out at the end of the equation. And it literally grabs the curve and slides it directly up or down the y-axis. It's incredibly satisfying to see the math translate so perfectly into the visual space.
Now that you've got this mathematical sixth sense, I'm going to leave you with this thought. How much faster will you crack your next algebraic problem now that you can actually see the shapes behind the numbers? When you glance at an equation and immediately know whether it's a climbing line or a sweeping parabola, you stop guessing and you start strategizing. You officially become a visual code breaker. So keep turning those dials, keep graphing, and I'll catch you in the next explainer.